point object being like a star, a distant star, like this one right, oh, sorry, whoops, like this one right here. Well, that's why I have a laser pointer, don't I? Yes, like that one right there. There we go, technology. If you have a point source, then the light will be bent around the planet, or around the closer star, and the star will just appear to get brighter. Whereas if you have a galaxy, you'll actually form a ring around the closer galaxies. So it's a little bit different from what you usually see of galaxies, but it's the same idea. But basically, if you have a planet, you're going to get more than one microlensing event. So the star is going to actually appear to get even brighter than it used to be. If the closer planet, or I keep mixing up star and planet. All right, if the closer star has a planet orbiting around it, the star in the background will actually get even brighter than it usually does. And then it'll get back to being regular. So you can actually see that bump. And based on that, you can derive the mass and the distance to that planet from the star, from the parent star. So that's kind of the pros. And this is extremely precise, probably the most precise method of discovering an exoplanet. However, there's a catch. It's extremely rare. What you have to have happen is a star with a planet orbiting around it pass directly in front of a distant star, a more distant star. So what are the odds of that happening?
And you have to be watching.
And you'd have to be watching at the moment that happens. And it only lasts for a few days. So only a handful of planets have been discovered this way, unfortunately, but that's the way it goes. So mostly this is a southern hemisphere technique because that's where the large and small Magellanic Clouds are. And the large and small Magellanic Clouds are these big kind of dwarf galaxies. They're full of stars, packed full of stars that are orbiting around the Milky Way. And you can only see those in the southern hemisphere. And since they're so densely full of stars, it's just like a higher probability that you would see one there. But again, it's just a really low chance event. And the other problem is that it's not repeatable, is it? Your star passes in front of another one, and it's gone. You can't have someone else go back and say, yes, we're going to watch it do it again. It doesn't work. So you can't confirm it or anything like that, for sure. But the last method that has been used successfully is direct imaging. So that's where you actually take a picture of a star, and you see the planet that's orbiting around it. So this is a Fomalhaut, which is a B spectral star, which means it's extremely hot, extremely massive, and extremely bright. It's up in the summer sky, so we could go out and look at it. And orbiting around it are several planets that have been directly imaged. There are only a couple of other stars that have been imaged that way. And the reason is that these planets are extremely far away from their star, so far away that the light from the star doesn't quite take enough away from it to block out the little planet. So as you can see, it hasn't shifted all that much in the last 2 years. This is an extremely huge orbit, so here's the planet right there. So again, this method, yeah. I mean, this is actually, I had another one that showed Uranus's orbit, but I believe it's right around in here somewhere is where Uranus is. Yeah, exactly. It's way farther than Pluto. Yeah, exactly. Don't get sentenced to prison there. You'll spend a long time. All right. So now I come to the exciting news about Kepler. See this line here? It shows you the eclipse of the planet going across there. And then there's kind of like a little dip that it's kind of hard to see. So they magnified it. You can see that the major dip right here is right there. And then there's kind of a secondary one. So what's going on is you can imagine that there would be a major dip of light in the star when the planet passes between us and the star. However, what I never thought about until they released this, and I don't think that a lot of people did, was you would get a secondary dip in light when the planet passes behind the star. Now think about that. The planet is reflecting light from the star, right? So how does a full moon happen, right? You know, a full moon is when the moon is on the opposite side of the Earth from the sun, right? And then a new moon is when it's on the same side as the sun from us, right? So that means that we're seeing the moon's shadow during a new moon, whereas during a full moon we're seeing the illuminated disk. So obviously when the illuminated disk passes behind the Earth, then we have a lunar eclipse. That's when we get the moon turning blood red, and it's kind of pretty. So the same thing happens on exoplanets. When an exoplanet passes behind its parent star, that reflected light is no longer there. So the star, the general field of the star gets dimmer. So that's what we were able to see there. This had never been seen before. Go ahead.
Say that again, it gets dimmer?
You're right, yeah. Okay, so I have this little image right here that actually shows Venus in its orbit. So when, I should have used that instead of the moon. So when Venus is on the same side of the sun as we are, Venus turns black because we're seeing its shadow, right? When Venus goes to the other side of the sun, if it's kind of off to the side, not directly behind it, we can see a pretty much fully illuminated disk. But when Venus passes behind the sun, we can no longer see that illuminated disk. Exactly. So we're not getting the reflected light. Exactly. We're not getting the reflected light. So that's what this secondary dip is, which is absolutely incredible. So the other thing that you might notice is that there's a trend line of the planet, or I'm sorry, the star getting dimmer and dimmer and dimmer toward the primary eclipse, and getting brighter and brighter and brighter towards the secondary eclipse. Does anyone want to take a guess as to why that is? Go ahead. Actually, they're not about the same depth, believe it or not. This one is extremely deep. It goes way down here.
I mean, not counting that.
It reflects more light until it hits.
Oh, I see what you're saying. Yeah, exactly. That dip is the same as this increase, right?
And then it drops off.
Yeah, exactly. That's exactly what's going on.
Reflectivity is increasing.
Exactly. So what we are seeing, what we are witnessing, is the phases of this exoplanet with the fancy name HAT P7, which, once again, they need to find nomenclature for exoplanets one of these days. We can't use Roman gods anymore because we're running out. Yeah, we need some Norse gods or something.
Judeo-Christian.
Yeah, Judeo-Christian gods. There's evil, yeah, exactly. All right, so let's bring it back here. So this is absolutely incredible. This is how precise the data is. Absolutely amazing.
So what was it doing?
Oh, what?
What was it doing? The different light dimming or whatever?
Oops. You mean like, why was the light dipping?
Oh yeah, you described it. You said any guesses? I knew you.
Oh, okay, yeah. It was the phases of the planet. So you see how Venus goes through phases as it orbits the sun because of how it reflects light? Yeah. So the planet, an exoplanet will do the same thing. So we get to see the phases of that exoplanet. All right. So now we get to the fun part, the big June data release. This was absolutely huge. I know now it is, but this is a couple of weeks ago. This happened a couple of weeks ago. Yeah, exactly. I mean, I don't need to tell you about it. You guys can just read it right there. So what happened was, before this was announced, there were a little over 450 exoplanets known in the entire galaxy, in the whole universe. We only knew of a little over 450. But all of a sudden, the Kepler guys announced that they had 706 stars that had candidates for planets. Now, I say candidates because they haven't been confirmed yet. We haven't seen multiple eclipses yet, or at least they haven't released that they have seen them. So they need to prove that. There are many things that can disguise themselves as exoplanets. Does anyone want to take a guess as to what one would be? What could look like a planet if you're doing the transit method? You're looking for a dimming of light.
A cloud of dust or
That's a good one.
asteroid belt.
Yeah, something like that. How about sunspots or star spots? You know, think about that. Yeah. So the way that you differentiate between the two is that star spots are ephemeral, so they don't last forever. They go away. But a planet won't. It'll just keep having the same orbit over and over and over again. So that's how you confirm it's a planet over a star spot, for example. But there are several other things that can disguise themselves as planets. So the locations of 400 of these were not included. That means that more than half of the ones that they announced, they didn't tell you where they are because they want to kind of hide them, keep their cards close to their chest while they analyze them because they're so interesting. The other ones are probably all just super Jupiters, the common thing that had normally been found. So most of these